In Chapter 6, we're going to start looking at chemical compositions and how to convert from these formulas we're seeing on the page to amounts that we can measure in a laboratory setting. We'll start by looking at the first three sections in Chapter 6, and I do recommend that you get out your copy of the periodic table, and if you have hard copy of the book, have that out in front of you, or if you've got the ebook, if you can pull up another screen to look at while you're doing this, if you're at all able to. That'll be handy as we're going along. So in the first section, they talk about sodium, how much sodium you're supposed to have in your diet. Now, sodium is important in our diet. We get plenty of sodium when we eat, primarily in the form of table salt or added salt in different packaged foods that we eat. Sodium is important to us. It's involved in the regulation of our body fluids, but if we get too much sodium, this can cause some people problems such as high blood pressure. So we want to watch our intake of sodium. All right, so what are we talking about when we talk about sodium and sodium chloride? How do we know how much we're getting? Well, the FDA recommends that the typical person consume less than 2.4 grams or 2,400 milligrams of sodium every day. Now, when they're talking about sodium, remember we looked at what sodium in its elemental state is. It's that soft, very reactive metal, that alkaline metal. Is that what we're consuming? Well, no, it's not. We're consuming sodium ions, but we can't get just sodium ions. We don't have just sodium cations floating around. We get them in the form of a sodium salt. So the mass of sodium we eat is not the same as the amount of whatever salt we're eating, so in this case sodium chloride, table salt. So if you measured the amount of table salt you were eating and assumed that was the amount of sodium, you wouldn't be correct. You'd actually be shortchanging yourself a little bit on sodium. 2,400 milligrams of salt is not 2,400 milligrams of sodium. So how do we know how many grams of sodium chloride we can actually consume and still stay within that range? So what we need to know is, first of all, what's the chemical composition of our sodium chloride? So going back to the last chapter, we know how to get from the name of the compound to the formula. Sodium, we write the symbol Na. Chloride comes from chlorine, so we write the symbol for chlorine, and then we look at their charges. Sodium is a 1 plus, chloride is a 1 minus, so I only need one of each of those to balance out. So I have sodium chloride. We have one sodium ion for every one chloride ion. All right, so you might think, okay, fine, it's a 1-to-1, so I take the mass of sodium chloride and divide it by 2, and there we go. Well, that doesn't work either, because the masses of both sodium and chlorine are not the same. If these had the same mass, that would work fine to divide by 2, but they're different. So we have to look at the relationship between the mass of sodium and the mass of sodium chloride. And we can't get it just from the chemical formula. We also need to know something about the masses of each of those. So we have to calculate how much of what we call a constituent element we have in a given compound. So whatever element it is we're looking for. So if we want to know the amount of sodium in sodium chloride, the sodium is the constituent element that we're interested in. All right, so how do we use those pieces of information? We're going to take the information we get from a chemical formula and the information we get from either the atomic or formula mass, and use that to calculate that mass of element within a compound. One example of that is what we're talking about, finding the amount of sodium in sodium chloride. Other applications you might be interested in. How much iron would you have in a given amount of iron ore? So here you can see an iron mining operation. How much of this iron-containing rock does it take to get a kilogram of iron? Because not everything in the ore is iron. We have to extract it and get rid of the parts we don't want. So, do we have to mine a couple of tons? Do we have to mine half a hillside? We can figure that out. Or how much chlorine would you have in a given amount of what's called a chlorofluorocarbon, so coolants. If you've ever heard of Freon 12, is a classic coolant used for air conditioning systems in refrigerators and car coolant and a variety of other sources. Well, one of the constituent elements in a chlorofluorocarbon, as you might guess from the chloro part, is chlorine. So how much chlorine would we have for a can of Freon 12, chlorofluorocarbon? We can answer these questions. Now, we're not going to actually answer these here, but we could if we were given that problem, and we're going to look at how we would do that. All right, the first thing we need to do is think of it in terms of counting by weighing, because again, we're dealing with these atoms and molecules that are submicroscopic. We can't see them. We don't have the luxury of just counting out numbers of atoms. And so we need to do it in a bulk manner, and that's not as unusual as you might think. For example, if you've ever gone to the hardware store to buy nails, now, if you said, I need 1,000 nails, do you really think somebody wants to sit there and count out 1,000 nails? I know you can buy a box that has that number in there. How do they do that? Does somebody sit there and count out those nails? Probably not. Probably what they're going to do is say, okay, what's the mass of one nail? Let's say the mass is 3 grams. Then if I need 1,000 nails, what do I need to weigh out? 3,000 grams, or in this case, we're measuring the nails in pounds. So they would know if this is 3.4 pounds of nails, they know approximately the number of nails they would have in there based on the mass of one nail. We can do the same thing with how many atoms there are for a given amount of an element. So in this case, we're measuring out carbon in the form of just black graphite. And they've measured out 8.25 grams of this carbon. So what if I wanted to know, what's the mass of, or not the mass, but how many carbon atoms do I have in that whole thing? Well, I can do the same thing as I would do over here. How would I figure out how many nails are in this 3.4 pounds? Well, I need to know how much does one nail weigh? Same thing over here. How much does one carbon weigh? If I know that, then I can figure out the number that are in there. So I had to go to those weights. So let's look at an example of this. Customer buys 2.60 pounds of a medium-sized nail. Now, instead of weighing out one nail, we're going to weigh out a dozen of these nails, okay? So we've got 12 of them. And I'm going to switch over to my pen here, just in case we want to write something. All right, so how many nails did this customer buy? I can figure out how many are in there. What do I need to do? Well, I set up my solution map. All right, so what am I given? I'm given pounds of nails. Okay, and what are some relationships that I know here? Well, they told me that it's 0.15 pounds per dozen nails, so that's 12 per 0.15 pounds. Okay, so I can write it a couple of different ways. I can write it this way: 1 dozen nails over 0.150 pounds, or I could flip it over if I needed to: 12 nails, 1 dozen nails. Okay, so I have these two relationships to get me from pounds of nails to dozens of nails, and then from dozens I have this relationship that shows me the number in a dozen to get to the number. All right, so how do I do that? I start with the 2.60 pounds of nails, multiply that by the 1 dozen nails per 0.15 pounds, and then I start out by pounds of nails canceling out. Now I know how many dozens of nails I have. Now I can multiply by the 12 nails in a dozen. The dozen cancels out. Now I have just the unit of number of nails. So I complete my math, and I find out that my customer has bought 208 nails. Okay, so pretty easy for nails. Well, that same thing would apply to anything. It doesn't have to be nails by the pound, but those conversion factors. The conversion factor for the first part was the weight per dozen nails, okay? And the conversion factor for the second part is the number of nails in a dozen. That will work the same whether we're talking about nails or atoms. If I can say the mass I have per a given number of atoms, and then I know for that number of atoms how many individual atoms there are in there, I can do the same thing. I can set it up the same way. So now instead of, counting by weighing nails in a pound, let's look at counting by weighing for atoms by the gram. We're going to set it up the same way. Okay, so when we're talking about atoms, we must use their mass as a way to count them. So as I said, you're going to need that periodic table because that's where you're going to get the masses of those atoms. Atoms are just too small, too many of them for us to count. So even if you could see atoms and you counted them as fast as you could, 24 hours, 7 days a week for the rest of your life, you wouldn't even make a dent in the number of atoms there are. Something as small as a grain of sand. We have to be able to use their mass to quickly multiply up. And we'll see kind of why that is later. There's going to be a challenge question I'm going to have you look at that I think will really kind of bring that home, how big these numbers are that we're going to be dealing with because of how small the atoms are. All right, so let's go to counting our atoms, or counting them by the gram. All right, so with nails, we used a dozen as a good way to measure them out. So instead of having to weigh out one little nail, we can weigh out a series of nails. Well, again, atoms, there's so many of them, even a dozen is too small. So we need some sort of grouping. We know a dozen is 12. You can have counting numbers for anything for groups. So for instance, you could have a gross of something. If you've never heard of this term, if you have a gross of pencils, that means that you have 12 dozen, or 144 of them. We use counting numbers for reams of paper. One ream of paper is equal to 500 sheets. So this is a familiar idea, actually, using counting terms to group objects. So for atoms, we need something that has a really, really big number for all these small atoms. And so what we're going to use, we kind of call it the chemist's dozen. It's something called the mole. Okay, so when we talk about moles in chemistry, we're not talking about fuzzy little animals. We are talking about a counting unit. Now, this is a little bit odd. The abbreviation for mole, M-O-L-E, is MOL. I know, really shortens it, dropping just an E, but that's the way it is. So MOL, M-O-L-E, that's the mole. 1 mole of anything is equal to 6.022 times 10 to the 23rd power. Okay? Memorize this number. Get to know this number. You will see this number over and over again. So just go ahead, commit that one to memory, tattoo it on your arm if you need to, whatever you need to do. No, don't really get a tattoo, sorry. But you need that number. All right, so a mole of anything, a dozen of anything is 12. A mole of anything is 6.022 times 10 to the 23rd. This number is also known as Avogadro's number. So we're not talking about green fruits that you eat guacamole. It's Avogadro. Amadeo Avogadro is the scientist that came up with this counting number. Now, this is, again, a counting number. It's just a unit. So you can have a mole of anything, just like you can have a dozen of anything. You can have a mole of marbles. You would have 6.022 times 10 to the 23rd marbles. You could have a mole of sand grains. You would have 6.022 times 10 to the 23rd grains of sand. It is just a counting number. Now, where did this number come from? It may seem arbitrary, just like, a dozen, 12. That seems like an arbitrary number. Well, there's a reason for a dozen. There's a historical reason for using 12 of anything. And by the same token, there is an actual reason, there's a measurement for using a mole of anything, Avogadro's number of anything. And we'll look at that coming up. But just realize that if you have 1 mole of anything, you can have a mole of atoms, you can have a mole of ions, you can have a mole of molecules, you can have a mole of golf balls, doesn't matter. Okay, but generally, if you have a mole of these submicroscopic particles, atoms, ions, or molecules, you start to get objects that are of reasonable size to be able to weigh. So for example, if you wanted to get an idea of what 1 mole of copper looked like, that would be equivalent to approximately 22 solid copper pennies. So the new pennies that we have today are zinc in the center with copper on the outside. But if you got a bunch of old pennies that were solid copper, 22 cents, you'd have about a mole of copper. Helium. If you had 2 relatively large balloons filled with helium, you would have approximately 1 mole of helium gas in those 2 balloons. So there's one reason for using the mole. We're starting to get up to reasonable quantities. We're getting to something we can measure on a real time basis in a lab. It's something that we are capable of actually doing. So where did that number come from? Why 6.022 times 10 to the 23rd? Well, the reason for that is because it is defined as, numerical value of the mole is defined as being equal to the number of atoms in exactly 12 grams of pure carbon-12. So remember, when we say carbon-12, we're talking about a particular isotope of carbon. We're talking about the one that has the 6 protons and 6 neutrons in its nucleus. Okay, so pure carbon-12, if I had nothing but carbon-12 atoms and I measured out exactly 12 grams of that, then I would have 6.022 times 10 to the 23rd. That was the relationship that Avogadro established. He used carbon as a convenient counting source. It was easy to access. He had a way of determining the mass for those carbon-12 atoms, and he was able to establish that relationship, that number. Okay, so that's where it comes from. What you need to know is that it allows us to count atoms by weighing them. So if I want to go in the lab and I know I need X number of carbon atoms, or I need X number of sodium atoms, anything, then I can do it by mass. I can do a quick calculation and say, okay, to get that number of atoms, I need this many grams of that substance, and I can weigh that substance out. All right, so let's look at an example of that. Let's say that I have 3.5 moles of helium. Okay, so remember, moles just a counting number. I could say convert 3.5 dozen helium atoms. So I have 3.5 moles of helium atoms. I want to know how many individual helium atoms I have in that sample. All right, so when we set this up, we take our given value, which is the 3.5. Let me go back to my laser pointer here so you can see this. Okay, so I started out with my 3.5 moles of helium, and what I'm trying to find is the number of individual helium atoms. The relationship that I have, I know every 1 mole of anything, doesn't matter what. In this case, it's helium. 1 mole of helium, 6.022 times 10 to the 23rd atoms of helium. So my solution map, I want to go from moles to number of atoms. My relationship here, here's number of atoms, here's the mole. So it is simply the 3.5 moles of helium times the 6.022 times 10 to the 23rd helium atoms divided by the 1 mole. Moles cancel out, and then I end up with 2.1 times 10 to the 24th individual helium atoms. Now, notice here we're just going from counting number from moles to individual numbers of atoms. This eventually we're going to be more interested in looking at gram masses, but it is important to be able to relate the counting number to the individual number in some cases. So we'll look at those examples first. Now, what if I want to go back the other way? What if I know how many atoms I'm dealing with and I want to know how many moles? Well, I would just reverse the process. I am given 1.1 times 10 to the 22nd silver atoms, and I want to know how many moles of silver atoms I have. All right, I'm given this number. I want to find number of moles, so now notice I just reverse it. Instead of moles to atoms, I'm going atoms to moles. Notice my relationship is now flipped over. It's the inverse of what I had earlier. Okay, so now instead of 1 mole of helium, I've got 1 mole of silver, same number. That does not change. It is the number of atoms in a mole. It can be, as long as it's silver here, or in the previous case, helium and helium, that relationship still holds. So now I set it up, 1.1 times 10 to the 22nd silver atoms times my conversion factor, number of silver atoms cancel out, and it leaves me with the moles of silver. So I have 1.8 times 10 to the minus 2, or 0.018 moles of silver. Typically what you're going to see when you're going between number of atoms or particles and moles of that substance is that the number of moles will be a smaller number, tends to be typically fairly small. The number of atoms is always very, very large in this case. Okay, so that's all well and good. We can go from number of atoms to moles and vice versa. That's like saying, okay, I've got 3 dozen eggs, I have 36 eggs. Well, that's okay if you're making a recipe that tells you you need, 8 eggs. So you can figure out the proportion of a dozen eggs that you need. I need, 8 eggs times the 1 dozen eggs over 12, so I need 8/12 of a dozen eggs in order to make my recipe. But what if your recipe, instead of telling you the number of eggs, tells you your recipe calls for 250 grams of eggs? And there are recipes out there that are like that. There are a lot of European recipes. What do I do if I need mass? Well, why would I need mass? Well, it may be, if I'm looking at mass, if I'm told I need 8 eggs for a recipe, do I need large eggs, small eggs, medium-sized eggs? 8 large eggs will give me a different amount of egg than will 8 small eggs. Or if you look at the example shown in the picture here, both of these pictures are a dozen nails. Well, if you were to, and these are relatively sized together, so if I held one of these nails up to one of these, it would be that much smaller. It's not zoomed in or out. If I were to take each of these dozen nails and weigh them out, do you think they would have the same mass? Probably not. These nails are much larger. We're assuming they're made of the same material, so these would have a much higher mass. This would be a lower mass. So if I were going to say, okay, measure out a dozen nails by weight, I would need to know which kind of nail I'm talking about. That's what we're talking about now. We need to know the mass of one individual one in order to be able to count up. Same thing for elements, just like the nails, large and small nails. Both of these pictures have the same number of atoms in them. They both have 1 mole of atoms. This is 1 mole of sulfur. This is 1 mole of carbon. You can tell by looking at it. It's on the same size container. This one takes up a lot less space than this one. If you look at the mass, the sulfur has a mass of 32 grams. The carbon is only about 12 grams. This is like the large nail. These are larger particles. These are like the smaller nails. They're smaller particles, so they take up less space and have less mass for the same number. So we need to start looking at molar masses and atomic masses. Those are going to become important to us as we do these number calculations. So we already talked about these atomic mass units. I mentioned those in Chapter 5 when you were learning how to calculate a formula mass. And a formula mass is going to relate to what we're doing here. Well, An atomic mass unit, or AMU, is defined as 1/12 the mass of one carbon-12 atom. The molar mass of any element, which is the mass of 1 mole of atoms of that element, is going to be equal to the atomic mass of that element expressed in atomic mass units. Okay? So, for instance, if I look on the periodic table, one copper atom has an atomic mass of 63.55 AMUs, atomic mass units, as defined above. Well, if I counted out a mole of copper atoms and put them on a balance, guess what? They have a mass of 63.55 grams. So therefore, we can say that the molar mass of copper is 63.55, or you might call it the atomic mass. If it's just pure copper, you would say atomic mass instead of molar mass. Okay, so when we are talking about atomic mass units, that is equivalent to the number of grams in 1 mole of something. Okay, so those are equivalent, and from now on, instead of using atomic mass units, you do need to know what they are. You need to recognize, if you see an atomic mass unit, what that is and what it means, what the definition is. But when we do calculations, the unit of AMU is not going to help you. The unit that you want to be sure and use is the number of grams in 1 mole. Okay, and that is the other thing that I will point out, because now what they've given us is a conversion factor. This is the same thing as saying 63.55 grams over 1 mole of copper. Or I could flip it over, 1 mole over 63.55 grams of copper. That's what this means. And so this gives us conversion factors that we can use. Okay, and we'll look at how we use those in a couple of slides coming up. All right, so let's explore this idea a little more. The mass of 1 mole of atoms of an element is its molar mass. So, sulfur. 1 mole of sulfur is 32.07 grams of sulfur. It is 6.022 times 10 to the 23rd atoms of sulfur. Carbon. The number, notice here, if I have 1 mole of something, I always have this number of atoms. The mass is what changes. For sulfur, 32.07, carbon, 12.01, lithium, 6.94. Okay. And you can see a trend here. The lighter the atom, the less mass you have in 1 mole of that atom. So, because 1 mole is always the same number, but the smaller the object, the less mass it's going to have. So the higher up you are in the periodic table, the smaller the mass. So how do we use that in a practical sense to carry out calculations? Now, let's convert between grams and moles. I am given a 0.58 gram diamond, and I want to know how many moles of carbon are in that diamond. Okay, so I'm given the mass of the carbon in the diamond. A diamond is nothing but pure carbon. I need to find the number of moles of carbon in that sample, in that diamond. So I'm trying to go from grams to moles, and this is where I use that relationship. There's my conversion factor. I look on the periodic table for carbon, and I see that the number for carbon is 12.01. That is 12.01 grams per 1 mole. So notice I always put that number from the periodic table with grams. Gram is the unit that goes with that, and that is always on a 1 mole basis from the periodic table. So 0.58 grams of carbon times 1 mole over 12.01 grams. Cancel out the grams, and I find out that I have 4.8 times 10 to the minus 2 moles of carbon in that diamond. Okay, now that tells me number of moles, and again, that may be useful for something, but what if I really needed to know how many individual atoms? And now I know number of moles, just like I would know how many dozens of them I have. So how do I get now, one more step down the road, to the number of atoms? So if I want to go from grams to number of atoms or atoms to number of grams, I can't go directly from grams to atoms, atoms to grams. Mass to number doesn't work. I have to go through moles. This is why moles is so important to the chemist, because it's the universal translator. Okay, I've got to get through moles to get to either one of these. I can't get there directly. So I can go from moles to grams, I can go from moles to number, but I cannot get from here to here. That does not work. Okay, it's always got to go through moles. So let's say I have, okay, this says pounds of nails, dozens of nails, number of nails, but what we were looking at is our diamond. So we started out with our 0.58 grams of carbon in the diamond, and this is what we just did in the previous slide, times 1 mole of carbon divided by 12.01 grams of carbon. Grams canceled out for us, and now we have the number of moles of carbon. Now we take that number of moles of carbon, multiply it by Avogadro's number of atoms per 1 mole. Now the moles cancel out, and I now have a setup to determine the number of atoms. So 0.58 times Avogadro's number divided by 12.01 tells me that I have 2.9 times 10 to the 22nd carbon atoms in that diamond. All right, so let's try another one. Let's look at one more example of that. How many aluminum atoms would I have in an aluminum can if the can weighed 16.2 grams? So if I'm looking at my problem here, here's my given information, 16.2 grams of aluminum. What I want to know is the number of aluminum atoms. Okay, so what I can't do is go straight from grams to number of atoms. Okay, that's what I want to do. I want to go from A to Z. Okay, can't go directly. There's no path directly there. I've got to take a detour and go through Mole Town. Okay, so I got to go through moles, and then from moles I can get over here to atoms. The road's blocked between grams and number of atoms. So I'm going to start with grams of aluminum and convert to moles using the molar mass. Okay, this number right here, where did this come from? This is from the periodic table. Okay, and you might see it even written as periodic table of elements, PTO. So if I ever say the PTO, I'm talking about the periodic table. Now I've got number of moles. Now I can use Avogadro's number to get from moles to number of aluminum atoms. All right, so I start with my 16.2 grams of aluminum. I multiply by 1 mole of aluminum for 26.98 grams from the periodic table. Those cancel out. Now I have moles of aluminum. Now you can work that out if you need to and then carry that number over, or you can just keep it rolling here. So whatever the answer is to this calculation, now I'm going to multiply that by Avogadro's number over 1 mole of aluminum. And now moles of aluminum cancel out, and that leaves me with just aluminum atoms, which is what I'm looking for. 3.62 times 10 to the 23rd aluminum atoms. All right, so this was a pretty quick introduction, but this is an absolutely crucial skill to build up as we move forward from here. This is what almost every calculation you will do in a laboratory setting will hinge upon. Getting from masses of substances, as you see in the periodic table, to moles of that substance, maybe to the number of atoms, but really going between grams and moles is absolutely critical. Knowing that you have to use moles as the universal translator is what is really critical. All right, now I said that we were going to have a challenge question to look at how big a mole really is. Okay, here's your challenge question coming up. If you had a mole of pennies, so Avogadro's number is 6.022 times 10 to the 23rd, how many dollars would every person on Earth get if you shared those pennies with them? All right, now the other piece of information you'll need to know is that what is the population on Earth? And what we're going to use is the estimate from 2013, which is that there were approximately 7.125 billion people on Earth as of 2013. So if you want to distribute a mole of pennies among 7.125 billion people, how much money in dollars would every person have? Okay, so try working that out if you can. We will take a look at that when we have our next Friday session. All right, so that concludes sections 6.1 through 6.3 of chapter 6. Stay tuned for 6.4 and 5. Yeah.